All right. Welcome everybody to our next session, modeling and coding part 2. It's just at 11:30 right now, so we'll give people a couple minutes to wander on in here from the last session or from a quick break, and then we'll get going. This is jam-packed, so I'll probably start pretty fast and go pretty fast. Maybe we'll see. Depending on the pace and any questions that I may see pop up or things of that nature. I may take a little bit more time to go through this notebook. The next section is supposed to be for going over and reviewing an exercise set. If we run long here, then maybe we'll just use that as the time to go through it, and then the solutions are posted as well. So if you have questions, we can answer them like in the Hoover app or something like that. But we'll see how time goes. Give another few seconds for folks to wander in, and we'll get started. It's loud. Okay. So let's dive into our second modeling exercise or example. And as I mentioned at the end of yesterday, that this is building off of the Opti201 second day example as well. So, and I asked, if you had some time to review that example, just so you can understand what the problem was all about. So I'll talk about it very quickly at a high level and talking about the important parts that are relevant for what we're going to talk about today. So this model and this problem was inspired by a predict and optimize technical challenge, where there was a prediction part of understanding solar forecasts, like how much solar availability am I going to have in a certain area over a certain time, and then optimize that from that. The optimization and the actual problem was much more complicated than what we have in Opti101 and in here. But for our purposes, it's essentially a problem of, we have a solar panel that has 2 batteries to it. We want to provide energy to a classroom building that has like a sort of fixed demand for running the building, but then also depending on the course scheduling that has already been set and figured out, and we're not messing with that. The energy sort of fluctuates over the day. Energy demand fluctuates over the day. So we want to use our solar capabilities, our storage capabilities, along with buying energy from the grid to meet demand. But we want to do so by buying the minimum amount of electricity from the grid. So we want to be sort of, I guess, as green as possible in one sense. So in that example, we also then said, okay, let's consider a different objective. So part of that was like, hey, let's see how easy it is to switch objectives and re-optimize. We considered a different objective where we then introduced a cost per time period for buying electricity, and then minimize the total cost. So it was a great way to see a comparison there to sort of see how priorities change. And we're going to look at that a little bit here as well. So now we're going to expand on this and talk about how we can do a few things that we just covered in the Hidden Gem session. So looking at multi-objective models, multi-scenario modeling, and then also solution pools. So here is the formulation from the Opti101. A lot of stuff here, but again, I'll sort of gloss over it and just talk about the important things. We have 2 batteries over a set of time periods that we need to supply electricity for. And let's see what else is important. We're going to talk about some things, and again, some of the decision variables that we have is the ability to decide whether or not we're going to charge a particular battery at a time or discharge. So are we taking in some of the solar, or are we giving some energy to the building? And we have some caps on the amount we can charge and discharge, and then we want to keep track of like the state of the battery, and that battery has a certain capacity, so on and so forth. So we have all of our parameters and all of these things again from the same problem that we went over last time in Opti101. There's all of the constraints. Again, it's a little, there's a lot happening here. But we'll talk about, I'll sort of dive into individual parts that are important as we need. So let's start running this notebook and see what we can learn. So let's first run anyways. It always gets me, it always surprises me. So what this chunk of code is doing is, installing Gurobi Pi, importing the packages, and then we're reading in lots of data and setting up lots of data. So we're reading in the solar forecast, reading in the energy demand forecast, or what we think that's going to be, and also parameters about the batteries, capacity, initial charges, and stuff like that that aren't really important for what we're going to be talking about here. Then we have our decision variables, run that, where we have our flow in, flow out, the amount that we buy from the grid, the state of the battery, how much we're using of solar for generation, and our constraints. Let's add those. And again, these are all from all from above, all the same things that we covered in 101, where we're making sure that we have a balance of power, making sure that we meet demand. So whatever comes in minus whatever goes out, plus what we buy from the grid, so on and so forth, that must be, and plus what we use from the solar panel sort of directly, that must be equal to the demand. And then for each time period, and then our battery state. So we want to keep track of how full our battery is. That's what these constraints do. Solar availability, making sure that we don't use more solar than we actually have. And charging and discharging. This was where we actually sort of saw some constraints that look like what we talked about more in depth yesterday, where we had binary variables. Then we have our objective. Make sure I ran that. Okay. We have our objective. And we also read in the price data and all that sort of stuff. So we have everything all set, good to go. Let's finally optimize this sort of base model. And I'm going to store some of these results in a data frame just so we can easily compare. So again, this is a scenario where we're just, taking in sun, putting it in batteries, possibly using that solar energy to feed demand for a building, and then using battery charging and discharging over a time period to meet all demand at and again, for this objective, we're minimizing the amount that we buy from the grid. So here's our solution. What I sort of highlighted is the amount that we bought from the grid, that's grid amount, and then also a cost that's associated with that. So now, again, seeing how easy it is just to change objectives, we have, I set up a linear expression for total cost up above. So now let's minimize the total cost instead. And I also create a copy of the model that we're going to use later, just so you know what that's all about. Oops, and I had this before. Sorry about that. This result should be below. So I'm going to just do this. So we can see, ta-da, there we go. So we can see the results of the optimizations. We can compare the two scenarios. So the first scenario, we're minimizing grid amount. This number is small or smaller at a particular cost. Second objective is let's minimize cost and not worry at all about the amount that we're buying from the grid. So actually we buy a little bit more, but we're being more efficient from a financial perspective. And so now let's actually dive into some of the new stuff that we're talking about. And we're going to use this information to sort of highlight some cool stuff that we can see from multi-objective modeling here. So you may be thinking, geez, this multi-objective, it must be kind of complicated. The answer to that is no, not really. It's actually very easy to institute a multi-objective problem. And again, during the previous session, we talked about two methods. One is a weighted objective, where essentially you'd have a bunch of different possibly a bunch of different competing objectives, and you just sort of mash them together by adding and by multiplying each of those objectives by a certain number, some weight, and then adding it all together. So essentially, you're taking several linear expressions and then making a linear combination of those linear expressions, and that's your new objective, and that's what you optimize. So we can see that's what we have right here. We're setting new objectives for our multiple, for a model M. The first thing that we're going to add is the total cost with a particular index. So this is so we can find it, and a particular weight. So we're going to weight the cost with the value of 1. And then we're going to weight the amount that we buy from the grid with the value of 10. Now, what these weights should be, completely up to you. It is a case-by-case basis. And obviously there's going to be some changes. If I change this weight down here to 5 or 2 or anything else, yeah, we're going to get different solutions. And that's fine. So that's where a little bit of subjectivity comes into this, is what are the right weights? How do I balance, how do I have this trade-off of, of the amount of energy that we buy from the grid? So a kilowatt, a kilowatt versus $1. How do I balance that? Obviously, you can just talk about the price, but if we're just worried solely on price, then let's do the optimization model before. So what this is instituting is saying, yeah, I really want, I am interested in having some lowish costs, but it's not my super high priority. So let's mix these two together in this certain way so that I have a little bit of the best of both worlds. So let's run this. And this is all it takes to add in the new objectives. And one thing that I want to talk about now is all of the objectives need to have the same sense. So they all need to be like minimizing or maximizing. So you just set the model sense for all of your objectives at once. So you may be thinking, whoa, okay, well, what if I have a min here and a max there? In your previous sort of thing, you just you just talked about, maximizing return on a portfolio while minimizing risk. They're going other ways. Well, it's very simple. If I wanted to switch this, then instead of total grid, and I wanted to minimize the total grid, if I wanted to maximize the total grid for some reason, then all you do is essentially you just negate the expression and put a negative sign in front of everything, and any min problem then becomes a max problem. You may need to mess with that a little bit just to make sure that you have everything properly sort of put together, but just wanted to highlight that for you as well, so that's top of mind if you're ever doing this. So we're going to set our sense for the model as minimize, and then optimize our multi-objective, and we sort of see that, hey, we were doing multi-objectives. We have 2 objectives. They're combined. So we're optimizing the objective, and it's weighted. So we sort of see that. So Gurobi, the output log, is immediately recognizing, okay, you have a multi-scenario problem. So let's let you know that I know that, which is good. And we look at the results from this, and we have, again, remember this first row was minimizing the grid amount. Second row was purely minimizing cost. And as you would expect, if you're taking sort of a balance of that, some sort of middle ground between cost and grid amount, that we would have a grid amount that's slightly higher than this one, and a cost that is slightly higher than this cost, which is exactly what happens in this example. So this is just one way to show how you can sort of balance these 2 objectives. Someone on one side may be saying we must minimize cost, and someone on the other side must be saying we must minimize the grid amount. And you could say, all right, let's smash these together in some way, be it with some weightings. Maybe you weight them equally. Again, that's up to you for the particular problem. But then you can say, okay, once we agree on that weighting, this is the solution that everyone should be happy with. So again, yeah, using this multi-objective approach, we were able to significantly reduce the cost from the first scenario, and while adding only a very little amount of grid purchase. Now, what I have an asterisk there, and what I want to note is, and we talked about this a little bit yesterday, in the first scenario, when we're minimizing the grid purchase, what we're buying, we're just minimizing the amount of energy. We have nothing to do with the cost. So there could be other solutions out there that are exactly the same, that have the exact same, that have the exact same grid amount, or super, super, super close, or something like that, that have a much lower cost. And we sort of just stumbled upon one here with with our weighted objective. So so if someone, so that cost of 803, that's just a cost that's being reported for this particular solution that is optimal, but we're not incorporating the cost into the optimization at that point. So so again, you wouldn't want to make any conclusions about what the cost would be, and there may be other costs. Sorry, let me rephrase it a little bit. There may be other costs that are lower for the same grid amount of purchase. That's the best way to say that. Okay, so that was an example of a weighted objective, and from the presentation that we just had, one of the one of the things that I highlighted was it's very easy to implement, which we saw that we just set a couple of objectives and we put a weighting in there, and that was it. But again, as I mentioned, there is some subjectivity to the weights. There can be some big changes in your solution with small changes in weights. That would take a lot of sensitivity analysis to sort of, running a lot of scenarios to see what that looks like, but it is possible. When you have binary variables, things, they're on-off switches. Sometimes you can get some decently large changes in some problems for by changing those binary variables. For this problem in particular, our binary variables aren't really changing a lot. It's whether or not you can charge or discharge your battery at a certain time. So it's really not a big thing. But if you're thinking along lines of like our example yesterday, where we're building facilities or opening production facilities, then yeah, you can have some significant changes with some small changes in weights from that. So the next type of objective or multi-objective approach is hierarchical, and I always stumble over that word for whatever reason. So if I do, pardon me. But again, as we discussed in Jem's video, then sort of what this looks like is you set a prioritization up saying, this is my first goal, is to do this. And then I have a second goal of this and a third goal of this. So you set a clear prioritization of your objectives. And essentially, as you go down those set of objectives, you're allowing for some degradation from the previous solution into the next one. So if your first thing is minimizing cost, which is what we'll do, and then your second thing is minimizing the amount that you purchase from the grid, then you're saying, okay, I want to minimize cost, but I want to stay in the ballpark. I want to be no more than a certain number of units away from that objective value. And that is what's setting one of the arguments of an absolute tolerance that we see right here. And then if you want to say, oh, well, then I want to be maybe 10% or 5% away, then that's a relative tolerance. So those are the two ways that you can limit sort of the degradation from that first solution into your when you move on to the second scenario. And then if you have a third scenario, which we will have in a minute, or a fourth, fifth, and sixth, everything works the same. In that third scenario, you have then two new constraints, making sure that I don't degrade too much from my first thing, and don't degrade too much from the second, so on and so forth. So let's make this problem a little bit more complicated, because that's what's fun. And let's talk about a battery's depth of discharge. And I sort of introduced this idea in the previous session. So it's for batteries, it's good to maintain their health, make sure that they run as long as they possibly can. And one way to do that is to limit a battery's depth of discharge. So you don't drain it all the way, and then put it and then charge it all the way back up, and you don't drain it all the way again. So there are batteries in which that is a way to maintain their health and make sure that they are useful for a much longer lifespan. So so one way that we can sort of start modeling something like that is by setting up sort of an event that's okay. I want to know when my battery is less than a certain threshold, and once it's less than that, then I want something to tell me. I want a switch to turn on that says, okay, we're below this certain level for depth of discharge. So that's a great way to introduce a binary variable. So we're going to say V sub BT is going to be 1 when battery B is below a certain depth of discharge. So we could say maybe it's 30%, 0.3 of its capacity, and then 0 otherwise. So what we want to model when we want to sort of add this and sort of keep track of this and relate this to the other decision variables that we have, because again, can't just say, hey, here's this V, here's what it stands for, and then just add V to the model and then be done with it. We got to add all the linking and to other decision variables and make all the logic go. So so what we wanted to say is if the battery gets below 30% its capacity, then indicate a depth of discharge sort of violation. Or we want our V variable to turn on. We want it to be 1. So writing that as sort of that's sort of if then in words using our notation. That's and as a reminder about our variables, the decision variable SBT is the state of battery B at time t. So so that is the essentially how much of my battery is filled up. So essentially we want to say if the state is less than 0.3 times its capacity, so 30% of its capacity, then we want V to be 1. So we can easily model this by taking the contrapositive of that conditional statement and using our good old-fashioned indicator constraints and go from there. So if we take the contrapositive, then again we negate both sides and flip them around. So if we're saying if V is 0, then our state must be greater than or equal to 30% of the capacity. Now here's where we run into a little bit of a problem in terms of doing this stuff in Colab and without licenses and just using the pip install thing. At this point, we sort of, if we were to consider both batteries, we would go over the 2000 variable limit. So for this next bit, we're only going to worry about battery 0, implementing this for battery 0. It would make a lot of sense to make sure that we do it for all batteries included for a problem. But again, since we run into this little bit of limitation, it's, we need to make do. So we're just going to consider this for battery 0. So let's start coding this up. We have our formulation. We have all this sort of figured out. We have our if then. We know how this should come together a little bit. So we define our variable V for time periods. Oops. Oh yeah, sorry. I was like, why did I just do time periods again? We're only considering one battery. So we don't need to have, again, I already forgot what I just told everybody. Is that we're only considering for battery B. So so we don't need to worry about multi-indexing this with batteries and time periods because of this. But if we wanted to implement this exactly as is, which I probably could have just put the both indices in there, just so we can see. But yeah, I simplified, and sometimes when you simplify, you may make things a little bit may make things a little bit more complicated, actually. But anyways, we don't need that battery index. So so let's define our variable V. I'm going to define a linear expression for the total depth count. You don't need to really do this, but I've started to get into this habit. I think it's kind of nice, particularly when it's actually more characters to type out than the actual summation. But here's the first thing that I want you guys to work on. I'll give you a minute to do that. Is let's implement this constraint again for battery 0 only. So you will need to type in quote battery 0 for some stuff. But implement the indicator constraint for this using V, and then using just so actually the name of the variable, even though I used like the notation here, it is the actual name of the decision variable in the code is state. So I'll make sure, so it's state like BT. There we go. Just so you know what is, you don't have to scroll back up and find it. That's the name of the decision variable that we established earlier. So do the indicator constraint. I'll give you another minute to sort of work through that, and then I'll plop it in and we'll go on. Okay, let's go. Let's move on and let's fill this in. So again, the whole reason that we did the contrapositive is we want to use an indicator constraint, and when we want to use an indicator constraint, the if part needs to be a binary variable, and then we need to have some other expression, some other constraint that we want to enforce when that first condition of the binary variable is met. So let's fill this in. So it's VT. Again, since we're only doing this for one battery, when VT is 0, then the state of battery 0 at time t must be greater than or equal to 30% of its capacity. And this is for all time periods in t. So now let's dive into a 3-piece objective, with cost being our highest priority, depth of discharge count being our second, and and grid purchase being third. So now if you think about what the depth of discharge, the way that we have it is the violation is when V is 1. So when V is 1, that's bad. So we want to minimize the bad. So this fits into the sense that, or it fits in with the senses of the rest of the objectives, where we all want minimization here. So if we had defined our V a little bit differently, we may need to like negate the summation or something like that. So what I want you to add in now is I added in a relative tolerance for each of these. Fill in the priorities based off of what I just sort of set up there, keeping in mind that the higher the number, the higher the priority. So take a second to fill in the priority number for each of these as well. This one is a little bit more straightforward. So I'm going to do the dangerous thing of not copying and pasting and actually typing while live coding. So this is again, so since we said cost is our highest priority, we can set that at 2. Our depth count is our second priority, so set that to 1, and our lowest priority is the grid purchase. Let's set that to 0 and optimize. Okay. So there's a lot more there's a lot more happening in the log here. So it's saying that we have 3 objectives, and we sort of see the process of what's happening here, and keep going. There's a lot happening. Okay, multi-objective solved. All right, awesome. So since we defined the linear expressions earlier on, we can use like the get value to get those individual results. So we could say total cost dot get value parentheses, that'll give us the total cost. If you want the number of grid violations, use that total dot get value, so on and so forth. But you can also query the objectives in this way, and I think this is a nice way to go about doing it, where you set a parameter to be the objective number, and you say, okay, I want to look at my first objective, and then I print the objective value. And the only difference between this objective value and the other way of sort of querying like an objective value when you only have one is that there's this n in there. So it's a subtle difference, but it gets the job done. So I already had the answers there. So we see that again, our first number was our cost. So our cost is again a little bit higher than I think some of the other values that we saw from previous two runs that we had. The number of discharge, the depth of discharge violations is 14, and the total amount of energy purchased from the grid is 1309. I just saw a question pop up that I think is good to answer right now. I try and pop up and look at them, so if I missed yours, it doesn't mean it's not good. It's probably really good, but sometimes I just see one. So it says, from the last video, does the multi-objective optimization work for mixed integer programming or integer programming problems? But that's essentially what this was built for, is looking at mixed integer programs and integer programs, as well as linear programs as well. So it works for everything. Well, I don't want to say it works for everything. It works for all of those. I believe you have to check documentation, and I'm not the best person to comment completely on this, but I think there may be some restrictions about non-linearities for this, but I don't know for sure. And we can ask, we have more of our experts here today. I can ask them and we can reply. Okay. So definitely I would suggest sort of messing around with the tolerances, messing around with priorities for the hierarchical. For the weighted, mess around with the weightings, sort of see what happens when you use different values. So there is subjectivity in how you feel these things should be prioritized when it comes to multi-objective optimization. So now I think we're about halfway through our time, and actually more than half. I use the slider bar to figure out how far I am through the notebook, but that's not the best thing, not the best way to go about it. But I think we're definitely good on time to work on the exercises during this session. But again, we'll make that call as we go. So the next thing that we're going to talk about is multi-scenario. And one of the things that I want to highlight about why multi-scenario is a really cool tool to use within using our functionality, using the Gurobi functionality, as opposed to setting up sort of separate scenarios and running that over and over again. So setting up 20 different scenarios and then running 20 different completely sort of separate optimization models there's a lot of goodness that goes on in the background when you have a multi-scenario optimization problem. So what Gurobi accomplishes in solving one of these scenarios, it's going to use in also finding optimal solutions for another scenario and then other scenarios. So you're definitely sort of I guess having your cake and eat it too. I think I used that yesterday too. Anyways, having your cake and eating it too a little bit with using something like this. You can I also talked about warm starts, and that's essentially what's happening. And I think I sort of described that in the last session, is you're more or less using like a kind of like a warm start from one to the next, in a sense. I think it's technically different. It isn't like it isn't actually using a warm start, but it is something similar. It's a similar idea where, hey, I have a solution to something, and it's kind of related to this other thing. So why don't I just start there? Or why don't I use this information? That's sort of the idea that's happening, what goes on behind the scenes. So let's actually finally get into some multi-scenario stuff. So I just sort of copied the whole model here. When it comes to the multi-scenario thing, idea, one thing that I don't do that I need to probably do a better job of in my models in Gurobi Pi is I always name my variables. I do, flow in is add vars, da da da. I don't do that as much with my constraints, and it's probably a good idea. I think it's probably a good idea to name a lot of these things, to store a lot of these things as objects to reference later. And this is what you need to do with the multi-scenario setup. So let's run this. It's building a clean model. Right now I am setting the objective to minimize the total cost. So that's sort of going to be our base case, and updated everything. So we're good to go. So what we're going to compare is we're going to compare 4 different scenarios. That's outside of the so 4 different scenarios, one of which is the base case, but a few other things that where we're going to change the objective coefficients, we're going to change variable bounds, and we're going to also change the right hand side of a constraint. So again, if you think about what a constraint looks like, it's decision variables, some linear combination of decision variables, less than, greater than, equal to some constant. We're going to change that constant. So the base scenario, just as above, the minimization, that's our base case. We're not going to change anything there. So while we're getting ready for this multi-scenario thing, we need to specify the number of scenarios. Say we're going to have 4 scenarios overall. I want to look at I'm going to establish, hey, let's look at our first scenario 0, and I'm going to give it a name, base model, and that's it. So we're not really actually changing anything from the model. I'm just sort of naming it and saying this is our base one. So the first sort of non-trivial scenario that we're going to look at is something that has mostly higher costs. So I added another column to the data frame that we import for the prices. Add another column, and essentially what I did was I took some number and said, if you're less than this number, randomly reduce the price. If you're higher than some number, then randomly increase the price by some percentage. So essentially the peaks get higher and the valleys get lower. So it's making the prices a little bit more extreme during instances in which the prices are high. Sort of like if you think about it like a normal curve, you're sort of stretching it out. And this could represent some scenario of energy company just surging prices during certain times while cutting prices during other times, something along those lines. It seems like but there's a bunch of different ways that you can come up with, like, hey, this is going to be my alternative price. But we're going to have mostly higher costs. Some of the costs are going to go down. A lot of them are going to go up. And the ones that go up are going to go up by a decent amount. So let's I sneakily added that to the data frame that we read in. So we're just going to take the price to column and set that as our second price. So now we want to move to the next scenario. So we say, hey, this is scenario 1. I'm going to name it increase price. And then how you actually change the objective is say for these, you have to use this for loop and go through each of these and say, and again, we need to think about what is the variable that is associated with the cost. So it's, even though we're talking about cost and we're talking about minimizing grid and other stuff like that, it's still the amount of energy that you buy from the grid. So it is our grid decision variable times the price. So if you think about it, how we would, and we did this yesterday, how you would, when you declare a variable in Gurobi, you can also set the objective value sort of internally to that declaration. That's kind of what we're doing here. We're saying, okay, for this variable, the objective for this scenario now is price 2. And oh, hi, Allison.
Hey, Jerry.
I just sort of saw out of corner of my eye pop up. So welcome. So that's how you update the objective function value for this decision variable and run through that. Oops. Oh, because I didn't run this. Let's see. There we go. Now we're happy. I forgot to run a cell. So there we go. So now we've established this scenario with a higher price. Scenario 2, lower battery capacity, also not great. Okay, so we're going to reduce the capacity of our batteries. One battery, I think battery 0 is 60. We're going to reduce it to 48. Battery 2's capacity is 80. We're going to reduce that to 64. And then it's the same idea. Again, we need to say this is scenario 2. We can name it. You don't have to name it. It's always good to name it. And then loop through the batteries and time periods and say this again, the state, we're putting an upper bound. When we say the capacity is 60 or 48 or 80 or 64, we are putting an upper bound on the state of the battery. We're putting an upper bound on the amount that it can hold. So we're change that upper bound. We say, let's change the upper bound of our state decision variable and change it to this other capacity that we just defined. So that is how we update bounds on a decision variable. And then the third scenario, or the fourth scenario, number 3, starting with 0 got me there too, is what if we, all these other scenarios where, oh, what if prices increase? What if our battery goes lower? Number 3 is what if we have more solar? Yay. What if we have more availability and our estimate is undercutting or something like that? If you actually look at the solar prediction data that we read in, there's a bunch of other columns that come with it. I sort of left the whole thing because it's interesting to sort of see the output of a profit time series model, which was what was used to develop the forecast. And if you want to know more about that, check the 101 folders on our GitHub, and maybe I can add the link to this as well. There's a whole notebook that goes through that process as well, if you're interested. For this problem, profit may have not been the best. It did, it has some odd things, but it was fun to use, so we just stuck with it. Anyways, there's a bunch of other values that come out from the output, not just say, this is my point estimate, but there's a lower estimate, there's that point estimate, there's an upper estimate, and then there's all these other columns that say, hey, here's kind of how we got there, through seasonality, through weekly stuff, through daily stuff, all that sort of, so let's say we want to take some linear combination of the lower bound, the center, or the point estimate, and the upper, and use that as our solar, say, maybe we think it might be a little bit higher, or, something like that. You can come up with these solar value, this sort of new forecast any way that you want. Maybe you have a completely different model, or, however you want to do that is up to you, but we have a new solar forecast. And I added this line here just in case if you had because some of the forecasts are actually negative, which again, kind of doesn't make sense. Let's just set them to be 0 so we don't have anything weird. And this is scenario 3. We're naming it high solar. And again, all we have is now it's the same idea as everything else. We're looping through and we're changing values to new stuff. And it's just the scenario N right-hand side. Because again, if you look at our constraint, we know that this is a right-hand side because all of our decision variables are on one side, and then our solar is on the right-hand side. The solar value is on the right-hand side, so hence we're going to change the right-hand side. So we have all of this. Great. All right, let's actually look at all of these scenarios, optimize, and go from there. All right, we're at the 15-minute warning. All right, it's telling me to hurry up a little bit. So we optimize, and we also then can start querying some of these things as well to figure out what the what values are for particular scenarios. And one thing that I want to mention is, I've mentioned this in the Hidden Gems video, I mentioned this a little bit earlier, is, there's smart things that are happening here. We're not just solving one scenario, pushing it over. Let's start and let's do a new scenario and then solve that, and then let's move that, and then let's solve the third one and then fourth one. You can sort of see even in the output logs that, oh, I've gone this far down. Scenario 3 has been solved. Let's use this smartness and let's just keep going. We have we're sort of solving a broader problem that has all of these scenarios sort of embedded into it. So we solve scenario 3 happens to be solved first, and then set scenario 0, then 2, then 1. So again, this is just sort of showing that there's smart stuff happening behind. I'm not the person to comment on what the smartness is, but it is there. Oops, and then where did this? I have something here that this didn't print out for some reason. I'm gonna just bring this down. It's printed out before. Is it hidden? I don't know. Anyways. I mean, it's not printing. I don't know why it's not printing right now. Anyways, this would pop out the scenario name and the objective value for that, but I'm not sure why it's not printing right now. Maybe it's because I have this. I do something silly. Nope, I don't know. I did something silly. But anyways, it'll be there. Sorry about that, folks. It printed before. So now let's, at the last few minutes before we dive into some exercises, or have some time for some exercises, solution pools. This is going to be pretty quick because I talked about what a solution pool was in the previous previous session, and talked about why it could be advantageous for you to gather multiple solutions. You may not have a complete sort of knowledge of what your preferences are for your problem. There may be new things for you to figure out, like, well, that doesn't make sense. I'd rather have this. And this tends to happen a lot. So maybe we need to institute this constraint or something like that. You just, and it's also a way to give maybe decision makers just more options, and some preferences just really aren't quantifiable. You may look at a solution here and look at a solution there and go like this, and like, I like this one better. I don't know why. I don't have a reason. I don't have a number for it, but I like this one. That's that's perfectly fine, particularly if they're both very, very good solutions. Maybe this one is the optimal, but we also pulled along its good friend here, and it also has, it could have the same objective value. It's possible, or maybe it has just like a very small degradation, but it's it's there. So we've just pulled a bunch of solutions, and maybe we want to analyze that. So here's how you, and also in the previous session, I did sort of talk about how you, like, when you set certain parameters, like the search mode to something, when you set it to 0, it's just going to pull all the solutions that it happens to find normally and store them. If you have it, at search mode 1, it's going to do something different. Search mode 2 is going to pull, I believe it's going to pull the best solutions, and all these parameters, we sort of discussed all of those in the previous session. So what we're going to have here is, we want the best solutions that are within a certain percentage of, it's within a gap of the overall optimal solution, and we want to pull 250 of them. So I ran that. So we're going to get 250 at essentially at most 250 good solutions that are within 5% of optimal. That's a pretty cool thing to be able to do very easily. And we sort of see, and we've seen this line has been sort of there a lot for us, and I've glossed over it every time. Even with the other examples where we had nothing to do with multi sort of scenario or adding solution pools or anything like that, just regular sorry. I was looking in on the questions real fast, and I'm going to finish, and then we can hop into those. I got distracted. So this pops up a lot. It was popping up in the examples yesterday, where it would say solution count 3 or solution count 5. So Gurobi's just automatically saying, hey, there's other solutions I got here, if you're interested. But now we're specifically saying, okay, this is the number of solutions I want. I want it to be within this tolerance, and I want the best ones. And if you were to set this search mode to 1, you wouldn't necessarily be finding, the best solutions. You would, this and this with 1 would be, just give me 250 solutions. Not necessarily the best. So now we have all of these solutions. What do you want to do with them? Well, let's put them in a data frame. And then what you can do is some data analysis. So essentially what we did here is we looped through all of our solutions, said, hey, I want to look at this number solution. So solution number I of 0 to 249. Query the information about the flow variable. So this xn is how you sort of extract the value of the decision variable. So we did that for flow in, we did that for flow out, across the batteries and time periods. And we sort of set up this nice little for loop that gives us all the information for all the scenarios about what goes in, what's charging, what's discharging for what battery at what time period. So we can do some additional analysis. We see that there's 90,000 rows from this. So there's a lot of, well, I don't want to say it's a lot of data because people may scoff at that, but that's not a lot of data. I agree, but it's a decent chunk. And you may be able to dive into this to figure and help you figure out some things as well that may be good for your problem. So we have about 8 minutes left. In this session at the bottom, I put links to this notebook, to the completed notebook, and then to exercise set 2, which is right here. Take the next 7 or so minutes to work through this, and then maybe we might, well, I'll hop in the others. We can all hop into the other Zoom session, other Whova session, to go through these. Maybe we'll start a little bit later going through it, but so going through the answers, so you have enough time to work on this. So we can end this a little early, and then I will see you in the next session, and we can go over a few of these answers depending on some time. So thank you very much, and I'll see you all soon.